Hi, this is Mrs. Roble. This is part 2 of ionic compounds and metals. So we, in the previous video, had talked about ions and how to name them and how to write formulas. Now we're going to talk about the properties of ionic compounds. Now, because of the bonding that occurs with ionic compounds, they are typically solids at room temperature. So you're going to notice a lot of the ionic compounds are like salt. They're essentially solids. Because of the bonding that takes place within ionic compounds, they have extremely high melting points. They also have very high boiling points, and that illustrates their stability. So ionic compounds typically are very strong when we look at the bonding. We'll eventually compare them to covalent bonds, and you're going to find that ionic compounds are hard to separate chemically versus covalent bonds. Now, as I mentioned in the previous video, ionic compounds tend to form electrolytes in water. And because they form electrolytes, they're very good at conducting electricity, and I should have shown you by now a demonstration illustrating why they conduct electricity. Okay, because the ionic compounds form solids, they are very hard and brittle. We're going to talk about metals and their bonding and why they have the properties that they have. As I mentioned before, the ionic compounds are soluble in water, and when they dissolve in that water, they actually undergo what we call dissociation, so they separate out into ions. So for salt, it would be sodium and chlorine. So this diagram here shows you what happens to solid ionic compounds. So if we were to apply a stress to them like a hammer, notice what happens is the ions shift, so the layers, they sort of misalign with each other, and when you have two like charges together, they actually repel each other. So this makes it easy for the ionic compound to actually separate and break apart. Okay, so this is an example of dissociation, and what happens is we have a universal solvent, which is water, and it's this small molecule here, and what it essentially does is it goes over to an ion within the solid. So this block is essentially a solid ionic compound, and when it completely surrounds an ion, it turns it into a liquid. So notice that water completely surrounds sodium ions. It also completely surrounds chlorine ions. So until that ion is completely surrounded by water, it won't technically be dissolved. At the bottom here is a dissociation equation. So we have sodium chloride, and notice that it separates out into sodium 1 plus and chlorine 1 plus. Okay, so now what we're going to do is we're going to take the information that we gained about the different ions and their formulas, and we're going to look at what we call Lewis structures. So Lewis structures, we're actually looking at the outer electrons. So here we have sodium, and it has one outer electron. Now because it's a metal, it's very good at giving up its electrons, and notice that it's going to donate its electron to the nonmetal, and notice there's one little space for the electron that sodium is donating. The goal for most nonmetals is to have 8 electrons. So please notice that the nonmetals, when they form the anion, they want to have 8 electrons around them, and we use this notation to determine how many electrons does the nonmetal have. Notice that after sodium donates its electron, it gets a positive charge. So it has no more outer electrons, and it assumes a noble gas that is in the row above it. So in other words, sodium becomes like the noble gas that's listed in the row above it. And then chlorine has 8 electrons. Because it has that additional electron, it has a negative charge associated with it. Okay, here's an example of magnesium, and it's bonding to chlorine. And in order for that to happen, we need 2 electrons from magnesium. But the interesting thing is, only 1 electron can go to chlorine. So because of that, we need to have 2 chlorines. And this is why I was drawing the equations that I was the other video. So here we have magnesium, which has 2 electrons, and notice only 1 of the electrons can go to chlorine. So we actually need 2 chlorine atoms for every magnesium atom. And this is how we essentially draw the Lewis or dot diagrams for the ions that are undergoing ionic bonding. So you're going to get very good at doing this, and I'll show you some examples and you'll practice on your own. Okay, so here we have aluminum oxide, and the interesting thing is that aluminum has actually 3 electrons and oxygen only needs 2. So in order to balance the charges, this is all about creating a neutral ionic compound. So notice that there's 3 electrons within 1 aluminum, and the interesting thing is, okay, 1 oxygen can take 2 of them, but that 3rd electron has to go to a 2nd oxygen atom. And then the 2nd aluminum will donate 1 electron to that 2nd oxygen atom, but then it has 2 left, and it can give it to a 3rd oxygen atom. So when we draw the dot diagrams, notice that we have 2 aluminums, and they have a 3+ charge each because they each lost 3 electrons. And remember, with nonmetals, the goal is to have 8 electrons. And notice that each oxygen has 8 electrons because it essentially gained 2 electrons from an aluminum atom.